Okay, this brings us to the concept of charging by induction. Charging by induction. So this word induction comes from induce. So we're talking about inducing a charge in an object. And the implication here is that we're not touching it directly. We're compelling there to be a charge in an object. So charging by induction. Now, this comes into play and when a balloon is stuck to the wall. So as you know, if you take a regular party balloon, you rub it against your hair, you can build up a static charge on that, which will cause it to stick to a wall. And we say, hey, it's sticking to the wall because of static electricity, which is true. But we want to get more specific with that and dig into it a little more deeply. So we have a balloon here, and we've been rubbing the balloon on our head. And when we do that, we literally scrape electrons off of our hair, and they stick to the balloon. Okay. Electrons come off our hair relatively easily because they're sharp at the end. They make a sharp tip, so the electrons hold on very tightly. So they get stuck to the balloon. Now, a balloon is made of rubber, so it doesn't conduct that electricity very well, and the electrons are just kind of stuck to the surface there. They don't really have any place to go. If you give them enough time, they'll slowly escape off into the air, but for the most part, they're just stuck there as a static charge. Okay, now what happens if we take this balloon and we bring it close to a wall? Okay, that's what we want to think about here. Now, the balloon itself has a net negative charge because it has lots of extra electrons on it. But the wall is neutrally charged. It's neutrally charged because it has the same number of protons and electrons in it. Okay, so neutrally charged wall, negatively charged balloon. Now, when we bring the balloon close to the wall, it's going to repel the electrons in the wall, and at the same time, it's going to attract the protons in the wall. So it repels the negative charge and attracts the positive charges which are in the wall. And there'd be no effect if those charges were not able to move. But as we said before, electrons are more free to move than protons are. And that means that the electrons get pushed away from the surface of the wall a little tiny bit. We're talking about microscopic distances. We're just talking about the electrons on an atom be kind of pushed off to the back side of the atom a little tiny bit. So we're not like sending the electrons out of the wall necessarily. We're just talking about them being shoved around within their molecules a little tiny bit. But the result of this is that the protons are closer to the surface of the wall than the electrons are, which means that the surface of the wall has a tiny, tiny, tiny net positive charge right there at the surface close to where the balloon is. Because the balloon, here we go, here it is. The balloon is inducing a small positive charge in the surface of the wall right where the balloon's going to be in contact. And since it's slightly positively charged, it attracts the negative charge of the balloon and the balloon sticks. Okay? So that is inducing a charge right in the surface of the wall, right where the balloon is touching. To summarize, the balloon has excess electrons, which means the balloon has a net negative charge. The wall is neutrally charged because it's been sitting there for a long time and everything's been able to even out. But when the negative charge from the balloon comes close to the wall, it slightly repels the electrons that are in the wall. The electrons don't go away because we're talking about a wall which is not conductive, like a wooden wall or plastic or something like that. The electrons are just pushed away very slightly. It leaves behind a slight positive charge close to the surface, which is enough to attract the balloon and make it stick. That's it. That's charging by induction. Now, we see charging by induction in other ways too. Okay, so in a lot of these diagrams here for charging by induction or all these charged objects, you often have charged rods, which is a rod which has a negative charge or a positive charge on it. You see this a lot. Now, the way these things are made or produced is if you take rods of different substances and you rub them with cloths made of different substances, or materials of different substances, sometimes electrons will leave one and go to the other. So in this particular example here, we have a glass rod, and it turns out if you take a glass rod and you rub it with a silk cloth, the electrons are not as attracted to the glass as they are to the silk. So electrons will get scraped off of the glass, and the silk cloth will wind up with a negative charge. And likewise, the glass will wind up with a positive charge. Now, if you did this in reverse and made like a plastic rod and rubbed it with fiberglass, then the electrons would be stuck to the plastic rod and would leave the fiberglass. So there's many substances here. There's plastic and glass. There's silk. Fur has different qualities. So you see this a lot, and they'll talk about a positively charged rod or a negatively charged rod is brought into a system. Well, that's how they make these things. Anyway, so in this case here, we have a neutral sphere, and we're going to have a negatively charged rod which comes in close to it. Now, I want you to predict what's going to happen to the neutral sphere when we bring this negatively charged rod into the neighborhood. We're not going to touch the sphere. We're just going to bring it close by. Okay? So think about it for a moment. And here's what's going to happen. The same thing's going to happen to the sphere as happens to the wall in the previous example. The electrons on the rod will repel electrons in the sphere, and you'll get a slight negative charge over on this side, and leaving a slight positive charge on the close side. So the sphere will be polarized. I mean, that's the technical term. You get a positive charge on the near side, a negative charge on the far side. Okay. Now, if you then take the rod away, then the charges in the sphere will even out and it will be neutrally charged again. But if you don't take the charge away, if instead you attach a wire to the far side of the sphere, then those electrons don't just go to the far side of the sphere, they actually escape and they'll go all the way to the ground. They'll go all the way to the earth because they're going to get as far away from these electrons here as they possibly can. Okay? And then you still keep the rod close by. If you then cut the wire, in other words, disconnect the wire from it, well, now those electrons have left the sphere and they have no way to get back. So when you take the charged rod away, you're left with a positively charged sphere sitting there. It's short of electrons and it's trying to get some back, but there's none to be had, so it just remains positively charged. Now, over time, you give it a few minutes or a few hours, electrons will find their way through the air and get back, and eventually it will be neutrally charged again. But for a little while, you have this positively charged sphere, and it's positively charged because the positive charge was induced by the negatively charged rod that was brought close to it. So again, the process is start off with a neutral sphere, even number of positive and negative charges evenly distributed. You bring in a negatively charged rod that induces a positive charge on the close side and a negative charge on the far side. If you then give those electrons some place to go, they will leave, leaving the sphere with a net positive charge. And then, yeah, so it leaves it with a net positive charge. You've induced a charge. Notice that charging by induction there's never any contact between the two objects. It's just pushing things around by electric forces in the electric fields. All right, we'll put that back here for next time. All right, so let's do a little application of this. Which one of these represents something that would happen? So we have three spheres that are all in contact with each other. They're touching each other, and presumably they were neutrally charged before we started this thing, but they're all in contact, and we bring in a positively charged rod into the vicinity. And we want to know how the charges will distribute themselves on these three spheres. So only one of these four options could actually happen. So look at it, pause it if you need to, think about which one it could possibly be. Okay, so I'm going to tell you the answer, so pause it if you're still thinking about it. The answer is option number 4 here. So since all three spheres are in contact with each other, the positive charge will be pushed away, the negative charge will be attracted. Really what's happening is electrons are being attracted to this side. and you wind up with negative charge here, neutrally charged in the middle, and positively charged on the far side. Now, if we then take away this rod, then the charges will redistribute themselves and all three will be completely neutral again. But what would happen if we separated the three spheres while this charged rod was still in the vicinity? So now instead of them touching, we keep them separate. We move them apart. We separate them from each other. Okay, what would happen? And then what would happen if we then took away this positively charged rod here? Okay. Now the answer is, pause it if you want to think about it more, that the answer is that this one would retain its negative charge. This one would retain its positive charge. This one would remain neutrally charged. Because if you separate them while the charge is being induced across them, then this one will stay positively charged. This one will stay negatively charged. And it will take some time for electrons to find their way from this one through the air, basically, over to this one. Maybe they'll crawl across the surface, across the ground, and come back up. But you'll wind up with a positively charged sphere, a negatively charged sphere, and a neutrally charged sphere if you separate them while this thing is still in the neighborhood. Okay. This is a very popular type of AP question, which you won't see this year because there's not going to be electricity on the AP exam. But this is a very common sort of a thought experiment that you see, and you will see when you take physics in college. Okay, moving right along. Now, what about this one? Here's another one. Let's say we have like a ping pong ball hanging from a string, and the ball is negatively charged. It has no pluses or minuses on it, so it's well, actually, I guess in this one it's unknown. We don't know what it is. It could be neutral, it could be positive, it could be negative. But we bring a positively charged rod into the vicinity, and we want to know what are the possibilities. Is this thing negatively charged? Is it neutrally charged? Is it positively charged? Could it be more than one of those? Okay, so think about that for a moment. Okay, pause it if you don't want to hear the answer right now, because here's the answer. The answer is it could be negatively charged, which obviously would produce an attraction, but it could also be neutrally charged, because this positive charge here will induce a negative charge on the close side and a positive charge on the far side, meaning that the thing will be attracted. So it could be negatively charged or neutrally charged, and it will still be attracted to a positively charged rod. Okay, moving along to the next one here. That's an old one. Okay, now we go to charging by conduction. Charging by conduction instead of induction. And the key idea here is that when you conduct charge, you're actually letting electrons or charges move from one thing to another. And to do that, basically, they have to be in contact. So very often, charging by conduction is when things touch each other, when they come into contact. Okay, so for example, suppose we have this sphere here which has a net positive charge on it. And we're going to imagine that the positive charges are able to move, although as previously discussed, they really don't. It's really electrons coming the other way, but never mind that. Let's imagine for a moment that these positive charges are free to move. Now, while they're separated, this will induce charges in the far one, but we've already learned about that, so we're going to ignore that for a moment. Now, when we bring them into contact with each other, these positive charges, they repel each other, and they want to get as far apart from each other as they can. So they will distribute themselves on the other object. And half of the charges will go on to B, and half of them will stay on A. And while they're in contact, they will distribute themselves at far ends away from each other. This is kind of that idea of charges tend to accumulate on points because well, that's just kind of what they do. And it kind of makes sense when you think of it in this term. If you had a positive charge here at the 2 o'clock position on A and another positive charge here at the 10 o'clock position on B, they would tend to repel each other and they would tend to crawl farther apart from each other. So they will tend to accumulate on opposite sides. Okay, now when we separate them, now B has a positive charge, and it acquired that charge because it was in contact with A. The physical charged particles were able to crawl from A onto B. It was charging by conduction, actually carrying charges from one object to another. And when you separate them, now they retain that new charge. A has lost some, B has gained some. That's grand. Okay, let's see what else we got. All right, so here's another one. There's a device called an electroscope, which are notoriously finicky, and I decided not to try to videotape me using the electroscope because sometimes they work and sometimes they don't. But what it is a two pieces of foil, like tin foil, aluminum foil, hanging from a rod, and then the rod extends to the top of whatever container you've got, and that's usually an insulated thing like a plastic shell or something like that, and then goes up to an electric probe that's up in the outside it. And the idea is that you can well, you can make those two tabs do interesting things. So, for example, here, if we start off with a neutral electroscope, and we bring a positively charged rod to it, it's going to repel the positive charges down the wire and to those leaves. And the leaves will separate because they'll repel each other. So you can tell if this thing is charged by what the leaves do. That's why I call it an electroscope. You can actually see the effect of the charge. Now, again, what's really happening here is electrons are drawn from the leaves up to the top of this, leaving a net positive charge, and that's why they repel each other. It's not actually positive charge moving downward, it's actually negative charge moving up, but the concept is the same. Yeah, so that's what happens. Now, if we actually touch the charged rod to the electroscope, to the probe up here at the top, then these electrons will leave the electroscope and they'll move to the positively charged rod. Electrons will move from one to the other, leaving a net charge behind. Okay, and then the effect of that is that the leaves will remain repelling each other. They will stay apart even when you remove the rod, because the rod has conducted some negative charge from the electroscope to the rod and carried it away. Now, another way to look at it, and it's difficult to prove which is happening and which is not, it could be that we are carrying positive charges to the electroscope, and those positive charges are traveling downward and distributing themselves along here. And that's why now there's a net positive charge and they repel each other. By the way, we call positive charge, well, now we'll save that for another day. We'll save that for another day. Yeah, so charging by conduction. We have conducted a charge to the electroscope and made things happen with it. Here's another one. Suppose we have a positive charge on a rod and we carry it to two little balls of cork. That's what they mean by pith balls. They're basically little balls of cork. Now, the balls of cork are initially neutrally charged. I'll move this thing back down here. They're initially neutrally charged, but when we touch the two cork balls with the charged rod, then it transfers charge to those and they will repel each other, just like the leaves in the electroscope will as well. So we are conducting a charge to the cork, and as a result, the two pieces of cork repel each other. Charging by conduction. This video has gone on long enough. So what have we done today? We have looked at electric charge, types of charge. We've learned what a fundamental charge is. We've learned about charging by induction and by conduction, and we will save Coulomb's law for another time. We'll do that in class next time because this has gone on long enough. Okay, thank you for your time. You have some homework questions that are assigned here that deal with these concepts, and we will see you next time.